Just a moment. Let me get the on the example in the Arduino. All right. So yeah, this one. Okay. So there is the code on examples. Okay, so what it did is first it set out the serial channels, and then later on it will get the analog input readings at the pin A0. And in our case, you can see that I connect to the A0, so it will get the readings at this pin. Then it will print this sensor value that has been acquired onto the at the serial monitors. Okay, and therefore let me just start the simulations, and we can see the serial monitors. The readings is initially is 0, and then if let's say I keep on moving up, what I'm going to get is 85. Okay, so 85 it just means that it is 85 out of 255. 255 stands for 5 volt, but 85 will be we need to make some kind of a calibrations, or so it means that let's say this is a float. Okay, instead of integer, I'm using a float. Sensor value will be equals to analog A0 and then divide by 5. All right, and then divide by 255, because there is a maximum value, and then multiplies all of them. I multiply by 255.0, and then I multiply by 5 volt 5.0. Okay, so in that case, I am going to get the serial readings. Okay, this is 0, and then you can see that now the maximum voltage that I am able to measure right now is only 1.67 volt. Okay, so it means that I actually lost sensitivity of this sensor. Suppose I'm able to detect up to 5 volt, but this sensor already like the sensitivity is already saturated by 1.67. Okay, everyone clear about this so far? You understand what I'm trying to talk about right now? Is everyone okay? Everyone okay? Any questions?
Doctor, can you explain what you did to the Arduino actually? I lost my connection over there.
All right, for this Arduino, actually I'm just performing a linear interpolations. Okay, I'm just doing linear interpolations. Right now, we know that when it is 0 volt applies at the A0, so at A0, if let's say I get a readings of 0 volt, and basically 0 volt, it stands for when A0 input receives 0 volt, I'm going to get a reading of 0. But then when the A0, I receive a voltage input of 5 volt, I'm going to receive a maximum value of 255. And therefore, if let's say this is the voltage I receive, and therefore what should be the, wait. So let's say over here, I receive a kind of readings. Okay, readings from the Arduino Uno, I get these readings, and therefore how am I going to relate these readings to the voltage? So that's a very simple linear interpolations, right? So what I need to do is just 5 minus 0 and then divide by 255 minus 0, and this is equals to V minus 0 and then divide by reading value minus to the 0. Okay, and therefore from here we are going to get that V divided by reading is essentially equals to 5 divided by 255. Okay, so voltage will be equivalent to 5 times reading divided by 255. So that is what I have keyed in over here. Just to convert the Arduino readings and then convert it into the voltage. Is that okay? Clear?
Okay.
All right. Because Arduino Uno could it received the input voltage range is 0 to 5 volt, but the sensor's output value is only from 0 to 0.416 volt. That's why the maximum that we can obtain over in the that is read by this Arduino Uno is 1.67 only. And therefore, to have full sensitivities, right, so that these sensor readings will be more sensitive to the change of the lightings, we need to have an amplifier. Okay, so this amplifier, we can just use any kind of amplifier that we have studied so far. We have the inverting amplifier and then the summing amplifier and so on. And in fact, you have already studied about this example, right? How to design the amplifier. So in this case, maybe I'll just do a very quick design, right? So this is an example. In our questions, okay, exactly like what we want to, just like this example, our sensors actually outputs a voltage which is ranging from 0 to 0.4 volt. And then we want to interface to this analog digital Arduino Uno. It needs to be in the range from 0 to 5 volt. And therefore, what should be the how can we set up this signal conditioning system? And therefore, first of all, we need to get this linear relationship. Just now, we have already done a little bit, but this one, I'm going to relate it more to the hardware. We want to get this amplification done by the hardware rather than the software. And therefore, we know that from the 0 to 0.4, it correspondingly, we want it to be 0 to 5 volt. And therefore, this is the sensor readings. And then that will be the sensor readings. And then this will be the signal conditioner. Okay, so 5 minus 0 divided by 0.4 minus 0. This is equivalent to X signal conditioning minus 0 and then divide by sensor minus 0. So by pressing the calculators, all right, so 5 divided by 0.4, this is equivalent to 12.5. And then we have a signal conditioning and then divide by sensors. So sensor output value, the signal conditioning output will be equivalent to 12.5 times sensor. All right, so this means we need to amplify the sensor output by a gain of 12.5. Okay? So far, so good. Any questions? Any questions?
No, doctor.
No? Okay. And therefore, in here, I'm going to amplify it using the 741. Okay, and therefore, what I need to do is I'll just get a breadboard. Okay, so this is the breadboard, and then later on, I'll just get a 741. Where is the 741 timer? 339 393. Where is it? Dual comparator. Here. Sorry. Okay, and therefore, I'll just attach it to here. And then, what I need to do is I just get two batteries. Where is the batteries? All right, this one. These are batteries, and therefore, okay, rotate it. All right, and then let's make it to be 4 batteries. So we have 6 volts over here, and then right, another battery. So this one I rotate it up to here, and therefore I want to generate the dual power supply. This and this connect together, and then this positive. Okay, it comes to here. So this is the red color. And then this is the negative power supply, or negative 6 volts. And it goes to here. This is black color. And eventually we have the ground. Okay, so this is the ground. Right, for the ground, let's make it to be green color. Okay, and yeah, this op-amp, I think I need to swap it. All right, so that it is more easier for the connections. And this is pin 1, 2, 3, 4. So pin number 4, it needs to go to the negative power supply. And then pin number 7, this goes to the positive power supply. Okay, and we want to achieve an amplification gain of 12.5. And there are 2 ways to apply this gain, 12.5. It could be either we use an inverting amplifier or non-inverting amplifier. So since I don't want to use 2 op-amp, okay, because inverting amplifier, I'm going to get a negative. And then I want it to be just a single supply. Not single supply. Just use a single op-amp, and therefore I think I'll just use a non-inverting. All right, because I just want to achieve amplifications only. So that means for this 12.5, for the non-inverting amplifier, we have a circuit that looks something like this. right? And then we have these formulas, and therefore 1 plus R2 and R1. All right, and this will be equals to 12.5. And eventually I'm going to get 1 plus 11 kilo ohm resistors divided by 1 kilo ohm resistors. Okay, actually, if I want to be more precise, I can get a 11.5 kilo ohm and then divide by 1 kilo ohm. But in real life, actually, we don't, for me, I don't think we need to be so precise. So most probably just 11K, and in this case, we are going to achieve amplification of 12 only. It's already more than enough, but at least it's much better than the previously without the use of any amplifier. So I'm just going to amplify up to 12 instead of the design. I mean the maximum 12.5 again. Okay, so I'm going to get the resistors. Okay, and these resistors 1 kilo ohm, and then another resistors I want it to be 11 kilo ohm. Okay, so this is 11 kilo ohm. And now I'm going to do the connections for this circuit. Right, we can see that from the output, it needs to go to the inverting, and then inverting, the R1 needs to go to the ground. Okay, so inverting, there is the resistors. Okay, so output pin will be from the pin number 6. This will give us the output pin. It goes to here, and then this needs to go to the inverting input, which is pin number 2. Pin number 2 is the inverting input. So this one I'm using a blue color. Okay, and then later on this 1 kilo ohm, it needs to go to the ground. Okay, so I'll just this is the 1 kilo ohm, right? Also over here, then it needs to go to the ground. So I'll just get this and then connect to the ground. Okay, and then the third thing is a non-inverting input. This receives the signal from the sensors anode. All right, the sensors. Okay, I think I'll just plug it here. Okay, and these sensors will. What is the value? What is the color? I think I'll just set it to be a pink color. Okay, so anode, there is the voltage will enters into the non-inverting and then amplify by these non-inverting amplifiers, and therefore the outputs over here is now there is pin number 6. There is the output, and it will goes to the A0. Okay, so I think I'll just do something like this. Okay, so it is connected to A0. Okay, as for this photodiode, okay, one thing we need to know that this cathode needs to be connected to the reference, so that it is part of the system, and therefore we just connect it to this ground. Okay. All right. So far, so good. Everyone clear about it? Clear about these connections? All right. So I'll just start the simulations, and let's see what is the reading that we are going to get. Oh, okay. This one I need to erase it. Okay, and start the simulations. Yep. So we get the. So right now, it is 0 volt, and if I keep on going to the maximum, okay, seems like I believe it is because of this. Yeah, negative, and then this one goes to the ground, and then this cathode and comes to here. All right. This is one thing that I'm afraid of. All right, let me check. This thing goes to the ground. Oh, okay. Sorry. I forgot one thing. You can see that this is a common ground, and then this one actually, this Arduino by itself also have another power supply. This is a power supply, and here there is another power supply. And therefore, if we want to connect it, all right, we need to common ground the system. So this is the common ground. I'm not sure whether can I do it this way. Okay. All right. So this V in most probably we need to power supply it by using this and this. Okay, so now let's see. I highly suspect. Okay, so now yeah. Oh, sorry. So right now, because we have already amplified, and that's why we don't really need to multiply this GAN anymore. All right, we just wait. Divide by 255 and then times 508. Yeah, we still need to get this. And then first of all, maybe just get the readings, integer sensor value, which is equals to analog read A0. E goes to 1021. Oh, okay. Analog input is actually 1021. Sorry. Yeah, the maximum value is 1021. So shouldn't be divided by 255. Okay, yeah. Supposedly it should be 1021. 1023. Sorry, not 1023. So what it means over here is actually when analog input it receives a 0 volt, and therefore we are going to it is essentially equal to 0 over here. This is the voltage. I mean AI analog input is this, and then so ADC values will be having a 0 integers, And then when the analog input is 5 volt, supposedly it should be giving us 1023. Okay, this 1023 is because it is a 10-bit resolution for the Arduino Uno. All right, and therefore we want to get the sensor value. This is, let's say this is the input voltage. There is a readings, and then should be the value, and therefore this is the formulas. All right, and it is able to convert it to this 5 volt. Okay. Up. All right, so from here you can see that basically, yeah, we have already the readings from this sensor is now 0 to 5 volt. Okay. Any questions from your side? Is everyone able to follow this? Is everyone okay? Clear? Yeah. So far so good?
Sorry, doctor, still trying to get the value.
Okay.
So far, I think maybe doing again or watching again, maybe I can get it.
All right, right. Okay, this is the code. Maybe for those who still want to work on that.
Is 4.99.
Yeah.
Okay. Good.
You I mean you divide by 1023, which is the maximum integer value for this DC, and then you multiply by this 5 volt, it will convert to the maximum to 5 volt. Okay. This circuit has some problems over here. It is not a very good circuit actually. This is not very good circuit. So, yeah, I think inverting amplifier is not a very good way. Non-inverting amplifier over here, it's not a very good way of doing this. So now we may also have use other type of another way, which is using the using the differential amplifier. Okay, so for this one, let's say I want to have an amplification by 12 kilo ohm. For the differential amplifier, we have this circuit. So this is 12 kilo ohm, and then R4 needs to be 12 kilo ohm as well. Okay, because R4 equals to R2, and then R1 and R3 will be 1 kilo ohm. So in that case, we are going to have a multiplication of 12. All right, so let's see. Right, this is 12 kilo ohm, and therefore we connect it to the inverting input output, and then goes to the inverting input, and this one pink color. And then resistors, we have 1 kilo ohm resistors. Oh, okay, 1 kilo ohm resistors, and these resistors, all right, put it here. And then let's have another resistors, and this resistor is 12 kilo ohm. And this 12 kilo ohm, which is the input, connecting from input, and then it needs to go to the ground. Okay, so this goes to the ground. Okay, and then we need to have another resistors, 1 kilo ohm, and this 1 kilo ohm from here to here. Okay, so it go so this is a differential amplifier, and therefore cutoff goes to here, and then anode goes to here. Right, so we are going to have positive minus to the ground, and therefore we should be able to get the readings. Okay, so in this case, if we, yeah, so we are getting much better readings. Okay, but over here it didn't reach up to 2.4. It only reached up to 2.4. It didn't go to the maximum. Okay, never mind. This one I need to figure out again. So I need to say that this one I'm still trying to get a more proper circuit for it. The main why it is so difficult is just simply because this op amp has to be double supply, dual supply. So it needs to have a positive and a negative power supply. And therefore, you can see that once it is dual power supply, this supposedly is having a voltage somewhere around 3 volt. So we are actually connecting 3 volt to this ground. I'm not sure what is the impact of doing this in the real life. And although simulation seems like there is no issues, but in real life, most probably you may damage your Arduino. So it's not a very good way of doing this thing. Okay, and unless we power it out, directly power it out over here. But this is also another issue, is that this voltage will be you are only receiving 1.5 volt. Okay, so never mind. Amplifications by this will not be a very good all right, you may actually do this, try it out. Okay. Mm-hmm. Okay, so I think we stop for a while. Let me think out whether is this circuit all right. Okay, just have a 5 to 10 minute break. Is that okay, everyone?
Yes, doctor.
Yeah, you may also at the same time try out with this play around and then with this circuit. Basically, the circuit that I provided to you is correct. The only problem is just that the common ground, all right, where this ground is it valid? So this one I need to think for a while. Okay, so we take a 10-minute break. Okay, is everyone ready?
Okay, doctor.
Okay, so shall we proceed?
Yes, doctor.
All right, so actually I have already I tried to figure out what is happening in this circuit. Basically regarding the common ground, later on in your when you are working out with your strain gauge, all right, so make sure that this your Arduino will be powered up by only 3. Okay, so in this case you can see that this tree is having four it has 4 batteries with AAA, so that means this actually give you 6 volt. All right, and 6 volt is already enough to power up the Arduino. And instead of power out using this USB, make sure you power out connect these batteries from 6 volt to this V in, because this is another way to power up your Arduino Uno. Right after you program your Arduino Uno, and then you detach your USB cable, make sure it is not connected, and then you just power up using this V in and then the ground. Okay, ground, it needs to be common ground. So it means that here there is the 6 volt, and then here is a ground, and then you just connect it to here, and you are going to get this actually a total of 6 volts over here. Okay. Maybe you are not sure about why it is 6 volt, then maybe I'll just all right, I plug it here, and then for this one I'll just plug it here. Okay, and if I run it, and you can see that it is actually 6 volt. Okay, because it's only coming from one battery. Another battery it has a common ground, but it actually connected to here, so that's why it the main use of this negative is just to power up this op amp, and therefore your Arduino is powered up by 6 volt. Okay, and then you can see that basically this sensor is a little bit weird. Okay, everyone. Could you hear me?
Yes, doctor, we can hear you.
Yeah, really sorry. Once in a blue moon, my computer could hang. So just this morning, I think maybe a little bit out of luck. Right. So let me sign into the Tinkercad. Okay, could you see the Tinkercad?
Yes, doctor.
All right. So basically, what I want to mention here is that you can see that for this photodiode, when it is not connecting to any device or resistor, I just measure directly using the multimeters. I could get 460 millivolt. All right. But what is quite unexpected is that if I connect it with the resistors, all right, for example, to this differential amplifiers, and if I right now I do the measurements, right, exactly from the for these two connections also, and you can see that instead of getting 0.5 volt, I'm getting 0.2 volt, almost half of it. This one I'm not really sure what is the impact. What actually causes this? I think most probably simply because this photodiode by itself may have some form of a resistance, and once you connect to here, and then this resistance and the resistors over here, they actually combine together, and that's why it gives you some kind of this very weird relationship. Perhaps you may use a voltage follower to isolate this the photodiode from the following from these resistors. Okay, most will use a voltage follower. Or what I'm doing here is actually I increase the resistance. Previously, resistance is I calculated it needs to be 12 volt, right? And multiplied by a gain of 12. All right. So since the reduction of the voltage, initially without connecting to here, I get 0.4, and now after I connect, I get 0.2 volt. So it means that I need to multiply by 2. So that's why the gain, instead of 12, 9, right now I multiply by 2, 12 times 2, so I get 24. Right. So in this case, I will be able to still get the voltage output in full range from 0 volt, right, complete darkness, and then complete brightness, then I get 5 volt. And then in between, I can get a different voltage as well. Okay. So far, so good. Everyone clear about how to use these sensors? And then also is signal conditioning in order to and then couple it with this microprocessor. Clear? Everyone? Is that all right? Or do you have any questions that you want to ask me? Why everyone so quiet? You are busy doing it, or you are still trying to understand?
I'm trying to do it, doctor.
Okay. So how is the,
Doctor,
yeah?
can you explain me again that why we did the why we made the resistance more higher than before? I couldn't understand that one.
Actually, it is not a very good way to increase it 12 kilo ohm lah. Yeah, it's actually not a very good practice. So I think I'll just change it back to 12 kilo ohm. All right. Uh, Supposedly another a much better ways of doing it is that I should use a voltage follower, so that I can isolate this isolate the workload of this photodiode from being affecting with interrelating with these sensors. All right, so I think in this case I'll just use another op amp. All right, so this op amps will be acting as a voltage followers, and then there is the output. Output comes to here, and then to this inverting, and this let's say it's an orange color, and therefore this cathode. All right, I think I'll just goes to here, goes to the ground, and then anode will just enters the voltage followers. Okay, and then this output, okay, instead of a differential amplifier, now maybe I'll just use a non-inverting amplifier. Wait. All right, I still use a differential amplifier. Okay, so this one goes to the ground. And this one anode will be entering one of the input. Wait, sorry. All right, this one will enter the non-inverting inputs. So use the orange color, and therefore output from this okay, and it will enter as here. As for this one, let's go to the ground. Okay, so supposedly right now I'm getting back yet 4 millivolt. You can see that it has already been isolated. And then for the coding, yeah, it's also 5 volt. Okay. Is that all right? But there is also another problem as well. You can see that the increment is actually not so linear. And basically, it just means that this is not isolated. Right? Okay, this one I directly connected to the ground. So this I directly connected to this inverting input at the differential amplifier, and supposedly I should add in another non-invert. The voltage followers, just to isolate this completely. All right. So this is something quite unexpected. All right, but anyway, I just hope that you get the concept, right? And then later I'll try to make a video on this. I think this is already worthy to make a video. Initially, I thought that I don't want to make a video simply because it's too simple. But right now, it seems like there are quite a lot of trap here and there. So I would like to, maybe later on, I'll just make a video on this. Okay, everyone. I hope you get some idea. Actually, this is not the main. Actually, this is not the circuit that I intend to show you. Right, I'm going to show you another circuit which is more related to your project. Is that all right if I move on?
Doctor, you will do a video, right? Or you won't?
I'll try to do a video. This one actually, simply because the sensor is produce a voltage, right? So this sensor actually acting just like a battery of solar panel. So that's why it has some difficulties to interact between different batteries. This becomes very ugly over there. So I think I will try to sort this out first, and then most probably make a video. If let's say I cannot sort it out, and most probably there won't be any video, because actually this one is not so related to your final project. Okay?
Okay, Doctor. We can proceed.
All right. So you can see that it actually, these sensors, it's a photoelectric. Okay, it's a photoelectric. It acts like a solar panel. This is one battery, and Arduino by itself also has a battery. I mean the power supply, because here you can see that USB actually power up this Arduino, and then later on we have another power supply which is from the battery. So that's why all these power supply, how all of them are interrelated. This represents a very ugly scenario. Okay, but anyway, I think I'll just ignore this one first for the time being. Okay. So what I'm going to show you right now will be another type of sensors, but this sensor, instead of generating the electricity, it will be generating a resistance. It's a resistive type of sensor. So photoresistors, all right. For the photoresistors, as you can see that, if I get these photoresistors and then terminal 1, I connect to the to these multimeters. And multimeters, instead of measuring the voltage, I set it to measure the resistance. Right, and then I start, and you can see that when it is dark, the resistance is actually 180 kilo ohm. But once I increase the brightness, the resistance quickly drop to 506 ohm. Right, so there is a kind of a resistance change when you expose this sensor to different brightness. Okay, so there is a photoresistors. Once the brightness change, the resistance will also the resistance of this sensor will also change. In fact, quite a lot of sensors are based on this resistive type of working principle. For example, like we have another sensors over here. For there is the flash sensor, right? For these flash sensors, if I connect it here, and then this one connect to here, and you can see that at 0 degrees, I'm going to get a resistance of 30 kilo ohm. But then if I try to bend the sensors and it gives bend to 27 degrees, I get 39. And if I keep on bending it, I have an increase of resistance. Eventually up to 163 kilo ohm for a 180 degrees bending. If I when 180 degrees, I get 163, and then if I didn't bend it, I get 30 kilo ohm. Okay, so it will be extending from 30 kilo ohm to 163 kilo ohm. Okay, so that is another kind of a resistive sensors. Even these force sensors, it is also resistive. All right, so I try to measure the resistance again, and you can see that initially when there is no force applying to this sensor, is actually the resistance is very high, right? But if I apply some kind of force, then you can see that the resistance actually slowly decreasing until the maximum of 1.2 I mean the resistance drop to 1.2 kilo ohm when you apply the maximum force onto this sensor by 10 Newton, right? And if I go the other way, if let's say no force is applied to it, and basically it forms a kind of an open loop, there is no connection. Okay, no, the resistance is so high that the current cannot flow through it. Okay, everyone clear about this resistive type of a sensor? So far so good?
So far, so good.
Okay. And therefore, how can we use, the signal conditioning for this resistive type of a sensor? So just take an example for these photoresistors. We have two types of a signal conditioning circuit that can work together with this resistive type of sensor. The first, most way we just use half of the Wheatstone bridge, which is the which is essentially a voltage divider, or two resistors connected in series. So in this case, let's say let's have a look on the voltage divider first. All right, so I have these resistors, and then I try to connect them in series, and then later on I get where is it? So I have a battery. So this is a battery. All right, so there is the positive. I connect this to here, and then the output from these resistors, I'm going okay, I think much better. It is much better I put it onto a breadboard, and you can have a clearer view of it. All right, so I have a resistors, and then plug it in here, and then I have this photodiode connected in series, and therefore I have this voltage supply entering the resistors. Okay, and output from this photodiode, I return to the battery. Okay, so this one is black color, and this one is red color. So what is the voltage output? Is that for this one negative? So I'll just go to the black. Okay, and then I would like to measure the output, and the output could be measured from the intersection point over here. Okay, and this one, let's say, is an orange color. So basically, this forms the voltage divider. Right. You all still remember about how a voltage divider looks like? The circuit for it, right? You all have any idea? No idea. Okay, I think I'll just let you have a look. All right, so this is a voltage divider. You can see that two resistors connected in series, and then the output is extracted from the connections between the R1 and R2. Okay, so this forms a voltage divider, and then the voltage divider can be calculated as this R2 divided by R1 plus R2, and then the output, voltage output, will be equivalent to the voltage input multiplied to this resistance ratio. Okay, so this is the voltage divider. Everyone clear?
Okay.
Clear? Any questions? You can follow, right? Okay. And therefore, you can see that over here, I have a one, sorry. So you can see that right now over here, I have one resistance, and this resistor is one, and then this is the photodiode, resistors. This actually also another resistors. So we have two connected in series, and the connection from the first and the second resistors, this is actually the voltage output. Input we goes to these resistors, and then output is coming from. And therefore, you can see that basically by using this form of a voltage divider, I can convert the resistance change into a voltage change, right? Initially, I get 8.95 volt when it is complete darkness, and then once I increase the brightness, eventually I will get a 3.2 volt. Okay. This relationship, you can see that is essentially non-linear because it's an inverse relationship. When it is dark, you get 7.96, a high voltage, and then when it is bright, then you get lower voltage. This is kind of a non-linear inverse relationship. And if you want to correct it to make it linear, you just simply swap the resistors. Right, so the first resistors, most probably I put it here, and then the second resistors, I'll just plot it to here. Okay, so in that case, the voltage, the output voltage is measured from the two resistors connected together. Yeah, that is here. Okay, so you can see that after I do these adjustments, right now it becomes initially when it is complete darkness, it is close to 0 volt, and once I increase it, then you can see that the voltage is also increased. Okay, but of course, if I change this resistance, maybe I increase the resistance to 100 kilo ohm, and therefore the voltage, we are going to get a different voltage. Okay. All right. So it seems like it's much better to use a 1 kilo ohm. Okay, so when it is 0, then we get 0. When it is complete darkness, then we get close to 0 millivolt, 0 volt, and then when it is complete brightness, we get 5.97 volt. Okay, there is a decrease of this voltage simply because of the resistance. Right, resistance, it has a decrease of voltage. It causes the decrease of voltage. Right. So far, so good? Clear? Clear about how to use a voltage divider as a signal conditioning circuit to transform the resistance change into voltage change. This one, everyone clear, right? So far, any questions?
Clear, Doctor.
Clear. All right. So now I'm going to move on with the something which is more related to later your project. That is how to use a Wisdom bridge. But of course, for the strain gauge, you are going to use the Wisdom bridge in is actually more advanced way, more extensive compared to this one. Right, so first of all, let us determine what is the resistance. Okay, just now, although we have already tried out, but I've forgotten what is the resistance range. So you can see that when it is complete darkness, we get 0 volt. Okay, shouldn't be voltage. I should be measuring resistance. Right, when it is complete darkness, I get a resistance of 180 kilo ohm. All right, this is darkness. And then when it is complete brightness, I'm going to get a resistance of 506 ohm. Okay. So if I want to use if I want to use what to say Wisdom bridge to convert this change to a voltage change, what I need to do is I just arrange this into a Wisdom in the form of bridge. All right, so I have 4 resistors, and then these 4 resistors I just connect it in as a diamond shape. All right, so I have this connected, and then here that is here. Okay, so in this way I have already formed the Wisdom bridge. And then for the once I have already obtained this, and then what I need to do is to get the battery. Okay, where is the battery? In battery. Okay, yeah, this is the battery. Okay, and then let's try to 4 batteries. And therefore the voltage supplies, let's make it okay, this voltage supply, let's make it to be green, and then this one comes to here. Okay, red color. So in this case, we have a voltage supply of 6 volt. This is the ground, and therefore the ground, let's move to here. Ground, and then for the power supply, it comes to here. Okay, so in this case, we have already obtained this Wisdom bridge. Power supply entering from top, and then at the bottom, it goes to the ground. And therefore, we have the VA and VB. Okay, VA and VB. And therefore, this is R1, R2, R3, and R4. All right, so since we have also photoresistors, and therefore, we may just eliminate one of these. Okay, and then most probably we just plug in the resistors into here, and then this one it plugs into here. Okay, so we just use these photoresistors in replacement of one of these resistors. And since these photoresistors has a resistance range from 180 kilo ohm to 506 ohm, and therefore maybe we can just we want to nullify the bridge when it is in the complete brightness as 506 ohm, and therefore this resistance, let's set it to 506 ohm. Okay, and in fact it's very rare to have a 506 ohm resistors. I think I'll just use a standard resistance 500 ohm. Okay, so this is another 500 ohm, and this is also 500 ohm. So supposedly, yeah, so 500 ohm, 500 ohm. So it means that when it is in the complete brightness, when it is very bright, so I'm going to nullify this bridge to become 0. But then when it is entering into complete darkness, very dark, then the resistance will, for this photoresistors, will goes up to 180 kilo ohm, and therefore break the balance of this bridge, and we should be getting some forms of readings. Okay, so far so good. Everyone clear? Clear about this? Wisdom bridge. Any questions?
So, Doctor,
Yep.
I have a question. So for now, we are trying to get the brightness, right? Through the brightness as a physical input, and the resistance change, we are changing to voltage change. All right.
Yep.
Okay. Okay. Okay.
All right. So right now the brightness, I set it to be the initial conditions. So it means that supposedly initially should be very bright, and therefore the whole bridge will be nullified and balanced to become a 0 to give you 0 volt. But then when you change the darkness, make it to be more darker, then most probably we will have a kind of a shift in the increase of the voltage. Okay, is that all right, everyone? Okay, and this is the Wisdom bridge, and usually Wisdom bridge, the output voltage will be very small. Let me get a multimeter just to show you. So actually for the multimeter is trying to measure a voltage difference between the voltage A and voltage V. So this is a voltage A. So we want to measure the voltage A, and then the voltage B will be here. All right, so now if let's say I start the simulations, and you can see that I'll get a negative 2.98 volts for the when it is complete darkness. But once I shift to complete brightness, it is close to 0 volt. It is not close to 0 volt just simply because the resistors I'm using is actually have some kind of inaccuracy or uncertainties, because supposedly I should use 506 ohm, right? So if let's say I use 506 ohm, right? Simulation, of course, I can get these resistors, but in real life, I won't be able to get these resistors. And you can see that once I get this 506 ohm, and the voltage is now further decreased because of is actually very close to 0 already. It's 1.28 millivolt. All right, but in real life, we can't really get such kind of a customized resistors. Standard resistors, most probably we are able to get 500 ohm. Okay. 500 ohm. So we get a much larger millivolt, negative 19.1 millivolt. But compared to the complete darkness, we are going to get negative 2.3 volt. Okay. So this negative voltage, it just means that we are trying to measure between the difference between VA minus VB, where VB is the reference. And in fact, if let's say we swap it, so it means that right now we make it to be VB minus VA, we are going to get a positive. All right, so this round we swap the VB and the VA. So right now it becomes positive is at here. Right now we are going to measure VB minus VA. So we are going to get positive 2.98 volt. And then if we change, and we are going to get 19.1 millivolt. Okay, so it means that actually this voltage offset, the polarity, it depends on how you select which one, VA minus VB or VB minus VA. This one is based on your design. So far, any questions, everyone? Okay, if no questions, then I'm going to add in amplifiers to amplify this voltage. Okay, but actually this voltage, you can see that is actually how to say, this voltage is actually already considered quite in the range already. So I didn't expect it to be such the voltage is already close to 5 volt. All right, so we have a 2.98, which is a 3 volt, and then we have this one. Okay, but anyway, I will just show you the complete circuit, right? To use it together with the differential amplifier. Well, first we need to get all right, so we are going to make it dual power supply. Okay, so this is the green. Okay, this is for the green, and then this is the negative power supply. Okay, so we get the black, and later on we get the op-amp 741. Okay, op-amp, and then swap it at here, and then we plug it in here. Okay, and then this is the going to the power supply, positive power supply, and then this pin number 4 goes to the negative power supply. Okay, and because this is we want to get a difference between VA minus VB. So why VA minus VB? Because VA minus VB, we get a negative, right? Just now we have already tested with the multimeters. And that's why if this one gives us a negative, and then we go through the differential amplifier, it also have a negative, then we are going to get a positive output, right? So let's get a resistors. We just want to perform the differentiations, and therefore okay, and then oh, I think I need to move it here. right, so this goes to the power supply, and this goes to the negative power supply. Okay, and then output comes to here, and this one goes to the goes to the inverting input. All right, so let's say the output, I'll just put it as a pin. And now resistors. Okay, output, and then another resistors going to the input, non-inverting input, and also another resistors for the non-inverting input. Okay, and then it needs to go to the ground. Okay, so that is for the differential amplifiers. And right now for the VA minus VB, so it means that VA has to be entering through the non-inverting amplifier, so that it will be minus with the VB. So VA, which is over here, it will enter to the non-inverting amplifier, non-inverting input, which is here. Okay. All right. And then for the VB will enter as the inverting input, which is here. So in that case, VA minus VB, we get VA minus VB is actually, initially we found that it's a negative, and therefore this negative afterwards will be inverted by this differential amplifier, and we are going to get a negative, positive. All right, so this goes to the ground. And then this one, we want to measure the op-amp output. All right, which is here. Okay, done. So that is how we can use the differential amplifier together with this op-amp. Okay, so you can see that right now we get a negative 4.77 volt, and then if we change it, we still get a negative. Have I made any mistakes? Yeah, this is 0, but here we get a negative 4.77. All right. VA, VB, negative and negative. All right, never mind. Maybe just we just do it by try and error. So this round I enter into the inverting amplifier, and then this one entering as a non-inverting amplifier, non-inverting input. Okay, and we are going to get a positive. Okay, and now let's go to the complete brightness. Then we get a 0 volt, and then darkness. Then we get a 5 volt. Okay, everyone, is that all right? You all clear about it? How to use a Wisdom bridge with the differential amplifier in order to get the convert from the resistance change into voltage change. Yep. So far, any questions? Yeah, of course, you need to revise it back. I know today I'm going a little bit too fast. I'll try to make it a video, but I cannot guarantee of it because recently quite busy But I'll try. Let's try. But anyway, I hope you all already grabbed the concept. Basically, that is the circuit, or maybe you can just snap the photo and then later on you can try it out yourself. All right.
That's it.
Yeah.
Just to clarify, if we okay lah, for example, the project. We take the project as an example. If I want to use a strain gauge, so my what? So the strain gauge will be at the photo that photoregister, right?
Yes. If let's say you are using one strain gauge only.
Okay. So it's
okay. But in the sensors, in the strain gauge sensors that you are going to purchase, it actually already have 4 strain gauge. So it means that you don't really, it is, I mean, the 4 strain gauge already arranged in the Wheatstone bridge. It is already in the diamond shape. So there is a reason why it is made in such way. In the following weeks, I'm going to go enter this strain gauge, right? And then you will understand much better why it is better in the form of a 4 strain gauge. Okay, there is one question. Is online lecture video you share in e-learning same with just now you teaching about? I have to say that the content is exactly the same, but the demo that I have shown you, the Tinkercad, the parts that is Tinkercad is not in the video yet, right? I have not recorded it in the video. In the e-learning, it is more like theoretical. It talks about the theory, it talks about the formulas, and then how to do the calculation, that's all. How to do the design. But the practical side, like using the Tinkercad, is not in the video. Okay? Any more questions? Okay, so if no questions, then all right, just a very quick trial. Let's say if I want to connect it to, I mean to get these readings by Arduino Uno and display it in the serial monitor. What I need to do is first connect this output. Okay, there is the output readings from the differential amplifiers, and then directly enter into the A0. Okay, this is A0. But you can see that once the current is actually output from the op-amp and then enter into the Arduino Uno, it cannot return back to the batteries over here. And there is a reason why we need to common ground this. All right, we need to common ground the power supply in this Uno with the battery. But there is one issue is that this common ground actually is also connected to another battery, which is with the positive. And therefore, this is the part that I am not really sure whether can we do that. All right. So I think most probably it is all right. It won't be a big issue if let's say we connect it this way. All right. So I will try to work that out and let's see whether is it going to damage the Arduino Uno, right? And let you know. Okay, so you can see that right now 5.81, it is larger than the maximum range of this Arduino Uno, which is only 5 volt. So you can see that it actually cut it, so that it only shows gets a reading of 5 volt. And if let's say I try to decrease it, and you can see that actually both Arduino Uno and the multimeters over here, it gives you the same, exactly the same readings. The only difference is just that when it is getting more than 5 volt, then Arduino Uno will cut it. Okay, 5.81 volt is still safe for the Arduino, right? Basically, 5.81 will not damage the Arduino, the input pin. But say the output voltage from this op-amp it actually reach up to 10 volt. 10 volt I think is still all right. It won't fries this Arduino Uno. But if let's say you get it larger than the 15 volt, then most probably this could damage the Arduino Uno. Right? This so make sure that the inputs at this A0 or the analog input of this Arduino Uno, it is always fixed to 5 volt. Don't get more than 5 volt. More than 5 volt, then it may be complicates the things. Okay. All right. Is everyone okay? Any questions? All right. So if you don't have any questions, just don't forget to sign the attendance. All right. I try to copy the links again, but most probably this link address will be look slightly different, but it's still targeting towards the same attendance link. All right. So don't forget to sign in the attendance for today's lectures. And if you don't have any questions, then most probably we could end this lecture already, and you are free to go. Okay. Any more questions? All right. So no questions, then that's all. See you all next week. Okay.